We get ready for our next presenter here, again, the AV Connected. I'd like to introduce Yasmin Almond up here, who we all just recognize for her incredible work here for running this event, and also being the person who knows how the AV works. So in addition to all of those great things, she's also going to introduce our next speaker, who we're very, very excited to have joining us today. So Yasmin, over to you.
Thank you all. It is my great joy and appreciation that I introduce you to our first keynote speaker. We're very excited to have him here. Dr. Zurbuchen is the Associate Administrator of the Science Mission Directorate at NASA headquarters, and he is tasked with helping us answer the big questions in life. Where do we come from? How did the universe start? Are we alone? The amazing images that Dr. Zurbuchen and his team revealed this week with the JWST have transformed, have already had a huge impact, and are definitely getting us closer to answering those questions. So congratulations on the first images from Webb. We're very excited, and they're generating incredible interest around the world, and we appreciate you being here on this very busy and exciting week for your team. So thank you so much, Dr. Zurbuchen.
Well, I am excited to be here. You hear my voice is a little bit hoarse. That's from all the screaming that we have. You're the advance button. Thanks so much, Kirsten, for setting it up and making this successful. We can spend this time however you want to. Let me tell you what I prepared, just so you know. But we can do a Q&A if you prefer. Or whatever format, but what I prepared is just kind of telling a little bit about James Webb Space Telescope and giving you a little bit of the science context, so you hopefully look at the image and see more than kind of the average citizen doing so, and then just talking through the images with you quickly, kind of telling you kind of a little bit what I see. I want to already tell you right now, this not going to do it justice here on the monitor. I hope you realize that all the data that we talked about yesterday are public. And you should have downloaded it already, and what you should do is really go zoom into these things, because that's where you really see how rich the pictures are. Of course, for those of us who look at these pictures, kind of the way I think about it is a storybook of planetary, actually stellar evolution and planetary kind of exploration, kind of as the future holds and is open up right now. So that's what I prepared. Do you want to do that, or do you want to do something else? Do that? All right, so, when Webb was started, something like 23 years ago, it was started with an idea, a science idea, that frankly had what you would call, kind of the way I will call those things miracles. And I don't mean to kind of talk about them like some people do. But for me, kind of every one of these missions that we have every mission that we do in science has at least one miracle. So it's a technology, a system, something we don't know yet what to do, and we're planning it in, and we're counting that will be successful. By the way, I don't want to do missions with 0 miracles. That's stupid. Because if you do that, what happens over time, especially if you do too many of those over time, you lose your leadership. Every time we do a mission, we want to do something that's really exciting, but we also want to open up the door for missions behind them. So we're constantly attacking that line that separates what we know what to do, how to do, from the line that is where most things are, which is no clue how we do this. So Webb was a feat of engineering in a sense that it had 10 miracles. Now, it turns out that's hard. Because if you look at the miracles by themselves through the lens of an engineer, you say, hey, there's 10 miracles, so let's just attack them with 10 times a bigger team. But if you thought that way, you have not understood system engineering. What actually happens is this miracle over here and this over here couple. So how you solve this problem affects this one. So the way you should think, it's always, if the number of miracles is n, the complexity goes like n squared. So if you go to 10, it's 100 times harder than if you have one miracle. So I just want you to know that's how that is done. By the way, that's a rule I use every time when I'm sitting there asking, can this mission be done, yes or no? I want to lean out, but don't want to fall on my face. And this was one of those things. So from the beginning, it was really focused on engineering. The next slide tells you why it was so hard. And you can't really see this. There's a circle over there, which is the primary mirror of the Hubble Space Telescope. By the way, it's like this. So from my toes to my arms, it's roughly 2.5 meters. That's what the mirror is. This one is 18 feet or 6.5 meters. Now today, if we said, hey, we want to launch that, does anybody know how to launch this? There would be hands going up. It's like, we have a rocket, perhaps under development, perhaps we already have it, that has kind of an ability of launching something that big. At that point, the answer was, we have nothing. The moment you say you have nothing, you need to change everything. Hubble was a mirror, a single mirror. This one has 18 mirrors. I already tell you right now, the first 3 questions are going to get some jewelry. This one, which is the most wanted jewelry right now, which is the format of these things. So here, ready, first 3 questions. All right, so so we had to fold that up. Miracle 1. And once you do that, by the way, you have all these 18 pieces. Each one of them needs to be adjusted with an accuracy that's way higher than as for a single mirror. Remember, they couple into each other, and the overall, just how optics goes, you need to be really, really accurate. So that's challenge number 1. The next slide tells you challenge number 2, which is really different. It's only the administrator. Does anybody want to answer it? Lori? I'm just kidding. So the challenge number 2 is the second one, which has had to be in a different place, right? It needed to be, Hubble, of course, in a low Earth orbit, so it flies over our head every once in a while, every good hour or so. This one needed to be 1 million miles away. Of course, it had to do that because what we want to do, and I'm going to tell you, is we want to build an infrared telescope, which is another way of saying we need a very cold telescope. You can't do anything like that by the Earth. There's just too much radiation. By the way, when you're around the Earth and going in orbit, the sun shows up every once in a while. So it's not just the Earth that heats you from below, it's also the sun that pops up. You cannot do that. So you need to go away, and L2, million miles away, kind of at midnight, look at where the sun was at noon. That's where the telescope is in the sky the day before, right? Kind of 1 million miles that way. So that's where we needed to go. L2 is not a stable point. It's a saddle point topologically for those of you who are nerds. So in other words, it takes fuel. So it's fuel limited, even if we go to L2. That's the point. The next slide tells you that so we have already talked about the mirror, but what we need to talk about is the sun shield. So even if you're back there, the sun and the Earth and the moon are now on the same, kind of on that side. So what you want to do is put up a shield that has the area of a tennis court. And even today, that doesn't fit into any rocket, right? So basically that's, so we had to do that. So kind of think Transformer, you know the movie. So kind of like, so in this case, it's not a monster when it comes out, it's a telescope that comes out. And it needs to come out from something that's very, very tight. I want to tell you that it was so tight that as we launched on the Ariane 5, there were 2.5 inches of space between the fairing and the spacecraft. Of course, we need that space because it's shaking on the way up. So we had the absolute minimum. We were within pounds of the maximum throw weight. So it's very much constraint driven. That's what I want you to know. Now, those of you who are system engineers, so I already told you one trick of system engineering, miracles couple, n squared, right? The other thing is the more constraints you have, the harder the problem gets. Now, the good news is innovators love constraints because what it does, it takes a lot of solutions off the table. So you can focus on the ones that are there, but you have to be careful to not add too many constraints. Otherwise, it's these math problems. You get the field medal if you solve them. It's so hard, right? So it's like, so you don't want that kind of problem. So this is close to that, okay? The next one is just celebrating that, of course, we launched that on a European rocket, one that, by the way, did such a great job that it injected us so accurately. Two things happened. First of all, we saw, if you watched it on Christmas morning, we saw the spacecraft depart and we saw the solar panels come out. If you listen to the voice, it said, oh, it will come out in 3 minutes. Then you saw it pop out. Well, what happened there is the rocket overperformed. The tip-off was so perfect that the spacecraft said, just like it was supposed to do in space, am I stable? Am I good? It said, yes, deploy. So the spacecraft made that decision, just like it's supposed to. It was 3 times faster than we predicted. And what happened is everybody around me was in tears because, of course, that day, that was the goal, to have the solar panel out, because if you have everything is good, the solar panels don't come out, you don't have a mission. So for that day, that was the goal, and it was waving goodbye as it went. So that was number one. Number two is it was so accurately injected that we have saved so much fuel that we're going to use to get it into the right orbit that it basically doubled the lifetime of the mission. So it's 20 years. Now, I want to tell you, before we launched, I told everybody we're going to want to partner with the commercial community to go fuel the spacecraft because it's stupid to build a mission for 10 years for $10 billion, right? Let's go fuel it. And the thing is, I stopped talking about that, not because I don't want to do that, but we have more time. Because, you know, kind of the trick about commercial interactions is you find the right when. Because, by the way, I want to do other things with commercial interactions. We're moving a lot of stuff forward. For L2, let's go solve some other problems first before we go to L2. And so there's going to be a time in 10 years, somebody, not me, people in my job don't live that long, in the job that is. So we'll say, hey, we need to now start working on a fuel. So that's what that is. Next. This is a picture of 3 nervous guys before launch. Just before the picture, I told everybody, I asked the photographer, can you take a picture so we can put it in the job ads, because all these 3 jobs will be free if it's not going well. The guy on the left is Stefan Israel, who's French. The guy in the middle is me. That to the right is Daniel Neuenschwander, who is Swiss. Now, I met with some Swiss ministers. I went for lunch, and I basically said, we should solve the major technical problem in Bernese German, which is the little accent where I come from, because we're both from the same area. I'm an official at NASA, he's one at ESA. The reason I'm showing you these pictures is at the leadership level, there's a lot of accountability, and rightly so. Some of you work up here, you should hold us accountable. That's our job, to do the right thing. We put our careers on the line when we do that, right? That's the other thing. So when you aspire to a job like I have, which I hope many of you do, because I told you it's going to be free sometime, you know, so you want to know this is really what you carry around. So before the launch, I carried the other speech in my bag too, because I was the ranking NASA official, and I had practiced that speech on camera the night before, which was the reason I didn't sleep all that much. So. This is how it looked as we went. December 25th moment, that is one of my favorite. Of course, it all went well. Next. And it left the rocket. Again, that panel came out just a little bit later, shining in the sunlight. And that's what was the goal of that day. Before we got the whole team on a plane and flew home. The story I'm going to tell you quickly is, of course, we worked on Christmas Day. And you say, how does that work? Have you ever worked with French unions? French unions don't work on Christmas Day all that often. And I want to tell you that not because I want to talk about unions. People should not work on Christmas Day. So that's it. So I'm not advertising that. But the French unions voted to work that day. And I asked multiple people, I thanked them, many of the employees that I met, and I said, why did you vote for that? He said, it's because of our American partners. They were here, and we want them to go celebrate with their families. And so for me, that's what teamwork is also about, is to sacrifice sometimes something that's dear to you so your partner gets that benefit. So not only is the partnership at high level, needs to be right, like the 3 people I showed you, at all levels, it needs to be that. Those are great teams. When you're in a team, you know that behavior happens. Next. All right, so kind of the biggest picture was my screensaver on basically every computer I had for a long, long time is the Hubble Ultra Deep Field. Of course, you know the story. You go look, take a drinking straw, point it to the darkest part of the sky, and look at that. In this case, it's close to the Big Dipper. It's in the northern sky, and you just integrate, in this case, for weeks. I already told you that Hubble is in orbit, so you need to put that week together over many months, right? Because you go behind and you're no longer looking north, it's day, you come back, you turn the camera back on. So it took a couple of weeks or so to get full integration, to get that picture, and of what it saw in that kind of little area, saw like 6,000 or so galaxies. When I did my PhD in astrophysics, we all had this galaxy catalog. We're no longer doing that, just because there's thousands, and and I'm going to show you it even makes less sense since yesterday, because we have that. What's really cool about this, of course, and I want to quickly, of course, tell you why we look at infrared using this picture. Of course, if you look at your neighborhood, you look at stars, they're emitting, just like our sun, in the visible light, ultraviolet. Stars everywhere do that. Now, if that star was in a galaxy that's away from you, what you'd have to remember, of course, is that the universe is expanding, so it's moving away from you, and just like the ambulance getting away from you and the tone dropping, that light is dropping towards the red and red to a lower frequency. If you go all the way back farther in time, the more you go, the more it drops. So everything, even though it's visible in the UV, when it started, it will arrive in the ultraviolet. Sorry, it will arrive in the IR, which is the infrared, which is all the way at kind of small heat signals. So if your body, kind of gets a heat signal, right? Your eyes are not actually the organ that is good for that. It's more your skin. The hot stove, that's IR. Even if you don't touch it, you feel the heat radiation, right? So that would be an IR signal. So you cannot see it. I was joking yesterday, let's all wear IR ties, which is none, right? I just basically say, so that's where we're going. So of course this had a little bit of IR, but not kind of all the way to the beginning of where the galaxies really form. And remember, there's one number you have to remember, 13.8 billion years is the age of the universe. Ask me later how we know that so accurately. John Matter and company got the Nobel Prize for that because of 2 other NASA missions. But there are, we know about that age. So what we're trying to do is find these early galaxies. Like, why do I care? Well, it's your history. The atoms in your body started over there first, and went through multiple generations of these galaxies and stars until they end up in your body. And on my hands, for example, we know pretty accurately since the last 5 years that the atoms here, one is platinum, the other is gold, came from merging neutron stars that explode, kind of merge into each other and create heavy metals. That used to be theory, we've measured it now. So my point is, you're made out of stardust, Carl Sagan said, and you're made out of these early galaxies. So you should be interested, it's your family history. Next. Already said that, next. This is, so I already gave you one reason you look at IR. I'm going to give you 2 more. The first one is, as I said, you look back in time, things shift to colder light. The second reason that is that many organisms here on Earth, but also stars and so forth, emit in IR. They're natural, just thermal emissions are in the IR, not in the visible. As you see, if something is warm-blooded, like up there, or something is cold-blooded, it's a huge difference in IR. Kind of in the visible, it looks like an animal to me in both cases, right? But the IR tells you what the temperature is there. So the same is true with objects in the sky. There's certain there's a whole galaxies we found that are only emitting in IR. Not only the old ones, even closer by. So we're all like, what is this? More to be discovered, right? So that's the second reason. The next one just tells you where it is in case you forgot. Next. The next one is the one that has to do with how IR propagates. And it is if we put dust into light kind of at the frequencies that are here, dust stops it. If you've ever walked in a fog, The best mountain hike looks really boring in the fog with your eyes because it just looks white. That means the aerosols in the clouds stop the light. If you saw IR, it would go through it. So basically what we're seeing is often through dust, through gases, to objects that we've never seen before. That's the third reason. So those are the three reasons we use IR. So now we've motivated that. I just want to tell you, let's go next. Let's go look at some of these pictures. You good with that? So there are galaxies. This is the new deep field that the president, released 2 days ago. The vice president there. And there's kind of 2 or 3 things I want to point out for you. So the most important object on this thing is a little red spot that almost you cannot see on this chart. Just look kind of by the beam, kind of half off the beam down there. It's a little red spot. It's a little speck. That is a galaxy that's over 13.1 billion years. That's why we built that telescope. By the way, we integrated light for this for 6 hours, not 2 weeks. We integrated light for 6 hours so we can do this many times per day or go much deeper, which is what we want to. First of all, so this little speck, besides that, you should know there's probably 20 to 25% more galaxies there. Why? Because we see deeper. So as we're looking deeper into time, we see more and more galaxies. But what you can see when you look at history, you see some crazy stuff. Do you see the bright cluster of galaxies here? That cluster of galaxies is when the light took off there, the sun just started forming here. So it's 5.5 billion years ago. So it's pretty far away is my point. So the light took 5.5 billion years to come here and tell us that. What happened though behind it, already 5 billion years before that, roughly at 10 billion, there was a galaxy, a red galaxy, that just was hanging out, minding its business. It's red now. It's just that it used to be a galaxy. Now I'll show you where that galaxy is now in the picture. Here. So I say, how can a galaxy be in more than one place? By the way, that's what we think right now. We need to analyze just to prove it's the same. Well, I don't know whether you've ever looked through a vase or a beer mug, right, at the dot. So if you have a complex glass structure, light goes every which way to get to your eye because the glass refracts the light. Well, what happened here, the cluster in front, like Einstein predicted, shapes space. The light is finding the fastest way to the camera, and it uses different trajectories, and it's so distorted, the galaxy becomes way bigger. So that cluster is almost like a magnification glass for things that are behind it. But it messes it up because the magnification glass is not perfect, it's a mess. So there's multiple pictures. So that's the second. So the most important thing is the most kind of very hard to find. The second most important one is there, and the third one is the one that needs to be discovered, which is, this is close to the record of the oldest galaxy, but not quite yet on there. I would bet, so I've been waiting on arXiv, the astrophysics publications. Within a day or two, somebody will probably beat. I mean, we just haven't looked at all of them, and we have not been able to do that. We have a telescope that can look at that field of view and kind of open little holes and basically do spectra for each one of these little galaxies. So we can do 100 galaxy spectra at once. So they're stayed out there, and we haven't had time to look at it because, of course, we want the scientists to look at it, not us. So that's what we're doing. Now, the final point I'm making about this is the field of view. Remember I told you Hubble is like a straw that you look through. This is a lot smaller. It's like a grain of sand stretched at my hand. So it's a lot smaller than you can look at a grain of sand through a straw, and this fills quite a lot of space. So there's more grains of sand. The reason for that, of course, is the primary mirror. It's bigger, right? So that makes the field of view smaller. That's not that profound, but just for you to know. So the sky is full of this. Billions of those grains of sand are out there. Can you imagine how beautiful the universe really is? And how much more beautiful since yesterday? I mean, for me, I just hope you don't forget, don't go and beat down the inner child, right? Yes, we can look at these things with our brains, but just forget that, look how beautiful nature is. And I never forget that. That's really important to me. I just want to tell you, also when we look at the Earth, look how beautiful our Earth really is and how beautiful the universe is. Next. All right, so we looked really far. The second one I'm going to talk to you about is the Carina Nebula. And so I gave an interview yesterday in Australia, remotely. I basically said, I'm really envious of you because you can go look at that nebula tonight. It's in the southern sky. So basically what you see here is something in our own galaxy that is a star-forming region. So remember, I talked to you about formation of first galaxies. Now I'm going to talk about formations of stars. I talked to you about the fact that kind of the way atoms get into your body is by multiple generations of galaxies and stars. So what is shown here is a birth site of stars. So do you see all the kind of brownish stuff with the structure that, frankly, so I always thought you could never do better than Hubble. Look at it. I mean, I'm not going to show Hubble. It's just flat, like paint. This one is like natural structure because, remember, we see through the dust, and we have more spatial resolution. So what you see is down here is a few stars died. For a variety of reasons, they died. And what they put out is something, by the way, we did not know when I started my PhD in the 90s, which is that there are complex carbon molecules in the universe. Not just at Mars, not just on Earth, in the universe. There was a lot of theories like, oh, complex molecules are really hard to make. Well, those are kind of strings, even rings of carbon molecules that are there. And of course, in infrared, they shine, right? Because the vibrational states of these rings are in our neighborhood, are in the IR. So you basically see these rings that are there, and they're leftovers from stars that went dead and kind of gave its mass, its new kind of complexity back to interstellar space. At the top of it, the reason there's such a strong boundary, there's a really bright set of stars that are baking off from the top. They're shining into this environment and baking off that gas, and it tries to kind of get rid of that complexity. Kind of UV, it cuts open these rings, these carbon rings, and it's not successful in all cases, right? Because down here, what happens, in that presence of all that, every one of these dots down there is a little baby star that's forming. So this is where it's important that you look at it at your own monitor, because what you're going to see is some of these look just like stars. Most of them are a little bit like the sun, both in mass and in type. But what you're going to see is some others that look like you look at a little disk from the side. So you're looking at the early days of a solar system, a stellar system being formed right there. So go look at these things. They're absolutely incredible. Again, we could not see those because the dust was in the way, and they're shining out and so forth. For me, it's one of the most beautiful pictures I've ever seen. Again, enjoy it as you look at it at yourself. Next. All right, so I'm going to go even closer, kind of, again, still in our galaxy. I'm hanging out in our galaxy. And what I just told you is that these molecules, they oscillate, and basically because of that, there's an infrared signal that is there. Well, what we can do is to use that very characteristic as planets in our galaxy are disappearing and appearing back behind their star. They're going around. And of course, if the planet looks like a billiard ball, that disappearance pattern is just a geometric pattern, and all lines of light disappear at the same time. Well, that's not what's happening here. If you have an atmosphere, the atmosphere disappears later than the planet, and therefore we can analyze the atmosphere by subtracting out the light. The kind of the difference of subtraction of the stellar light gives us the atmospheric signature, which is shown here. And the wavelength is there, and what you see is a curve that says, hey, there's a lot of water there. That's exactly what we expected for this planet. What we didn't expect is, by the way, it's basically a mini Jupiter. It's half the mass of Jupiter within Mercury distances. What we didn't expect is that the amplitude of that signal is a lot smaller, which tells us it's cloudy or hazy. So the publications of the people that said this is without clouds, wrong. By the way, that's science, right? Things that are wrong, you know you're in the realm of science if things are wrong. So that's good. The one thing that we're also not telling you is, so this goes to 2.75 microns. With that chart, there's another chart like this that we have that we just haven't been able to show you yet. So there's way more analysis that we're going to use for that. My point is, just imagine all the molecules we're going to find here, including the molecules, of course, that shaped the Earth atmosphere once life arose. Our atmosphere really changed once life showed up. As bacteria initially, and really shifted the atmosphere, and that's what we're going to look for in these other places, because in our mind, when we look at the night sky, it's not just looking at the stars, we're imagining somebody else looking in your way, right? That's what I do. So as far as I'm concerned, finding life elsewhere and kind of sites of life is really what this investigation is about, and this is a demonstration of the capability. The next is I showed you about the nursery of stars. This is the death of a star. So imagine 10,000 years ago, a star burning its fuel and it exploded. The way it exploded, it's actually not like a supernova, it's the wrong word. It shedded its surface, it pushed off its surface. Kind of 10 miles per second and moved away. And it didn't do it in one single push. It did it in multiple kind of parts that are out there. That's what you're looking at right now. So at the middle, it was a kind of a sun-like star. By the way, that's what the sun will look like in 5 billion years or so. I think the vice president asked me, when is the sun running out of fuel? And I said, it's not your biggest problem. But so it's 5 billion years. So the sun runs out of fuel then, and basically is shedding. So at the center there is a white dwarf, which is basically the leftover core of that sun. And then going forward, in its leftover there, what we found at the lower frequencies, we actually found there's another star there that's also about to die. So there's a second one coming that is there. I think that brought us to the end of all the images, right? And so I want to get rid of my 3 questions. All right. So 1, 2, 3. The others who have the hands up, could somebody just take a note? Now it comes more. Let's go bring a bag of these things later today. Can somebody drop it off, Andy? Yeah, I have a bag at my office. Okay, the people I pointed out, ask the question.
So
Here.
I feel like everyone's going to be slightly disappointed with my question. Just to reintroduce myself, I'm Audrey Scott, fall intern current Ravel and Sella. But more importantly, this question is I just wrapped up my sophomore year of university studying astrophysics. And a couple of my professors were on the Astro 2020 Behavior Survey. So as a result of that, my question is, what is the expected timeline to address the calls to action in the 2020 Behavior Survey, given Rogan's current development to Webb's deployment in response to
So the expected time scale in a normal kind of environment is 2 years or so. That kind of our budget should reflect the decadals. You may or may not have noticed, right? The decadal is not the only thing that drives budgets. So there's constraints that come from elsewhere. Priorities that are elsewhere. So what we're going to do in the next years, and every year we're going to look at the decadal. The way we look at the decadal is less about kind of saying here's what we must do. It's more about of money that's available, what are the highest priorities we use it? So kind of the way we use it, we have a mission. If we get into trouble, if we have more money or less money, we use the decadal to prioritize science against science. But 2 to 3 years is usually the right answer. But in some cases, there have been decadals that took 5 years for them to get started. The heliophysics one is one of those, and we're basically close to the end of it. So we managed to ramp up really quickly, so we get most of the priorities off the table. So it's not always the same as the short answer. Who was the number 2? Go. And then you.
My name is Simran. I'm working at Planet this summer, also representing the results section. With the images, there's one
Well, I mean, I think for me so I recently was invited to a philosophy TV show, which was really cool. I thought that's going to be a dud. And I really enjoyed it because the questions that were asked, this question I should think about more. And it's that question. Not just in a science sense, but how does it change for humanity? I want to tell you why I studied astrophysics. It was after a class of the Copernican revolution. The fact that you can look at the sky and realize that the Earth is not in the center, but the sun is in the center, changed not only how we look at nature, it changed how we perceive ourselves here. It had a huge destabilizing effect of the power structures on Earth. I think looking at nature, that helps us change not only what we know, but how we live, how we think about ourselves. It's just incredible, whether it's our own Earth or that. So with that in mind, what is the thing that could most change how we think about ourselves? It must be life elsewhere, right? Because I think that's going from one life in the universe to many lives in the universe. It's just incredible leap. So for me, everything that's moving in that direction must be the answer. Go for it.
My name is Andrew. I'm interning with I was a future space service fellow last year. So first of all, thank you so much for coming to talk to us. Late, but I've had a variety of friends and family texting me past like week, freaking out about me. With that said, you mentioned earlier in your talk that
So I think what's really important to realize is how we're using the time on the James Webb Space Telescope. And I think we're actually using it the right way, which is that we're not prioritizing a political process, what the right ways of looking at it. We're asking the whole world, what are your best ideas? And we're analyzing them by reducing or eliminating, to the best of our ability, implicit bias, which in this case actually has a lot of early career and very much at parity between genders. Investigators that tell us that these are the highest priorities. So there's a number of follow-ups that we're going to do. TRAPPIST is one. Remember that planetary system around a red star, a small planetary system, 6 planets, 7, I think it's 7 now, that 3 of them possible in a habitable zone. We're going to analyze those, looking for atmospheres, because it's many planetary systems. We already told you the deep view that we're doing here. We're also going to look at our own solar system. We're going to go with Clipper in 24, looking at Europa, and I really want to know whether there's water spurting out of the kind of cracks in the ice or not. And if the answer is it is spurting out, that's really different for how we want to fly the mission than we perhaps currently plan. So those are just 3 examples. There's many more. All of these are in the first year. You know what's really exciting? What's going to happen in year 3. So first year is entirely driven by our expectations. I like the lead scientist yesterday saying the science community was too conservative. But the science community said, we can probably do 3 targets. We know they could have done 10 for the price of 3, but now they're not planned. So the second year will fix that. But see, the third year is the interesting one, 3, 4, 5, because we're going to ask questions that we currently can't ask yet, because we haven't actually understood that the questions that we're asking are the wrong ones. That's what always happens with these telescopes, right? So for me, the coolest stuff, those of you who are still students, those of you who are still out there, focused on, your careers, but also students right now in high school, or even younger, questions are many. And we're going to follow up on things of other missions I've done, but also of this one. How am I doing on time? I want to make sure I don't overstay my welcome. I really like our armed forces, so I don't want to have them wait. One more question? Go. So look, basically for me, the way I look at all of science, including astrophysics, I'm asking, how do we do the best science per dollar? And in Earth science, there's many programs we've already started where the best science per dollar is not for us to build the mission. It's for us to buy data from missions that are already built, perhaps for a different purpose. And we're going to do that. We're going to continue to double down on that. What's also happening is space companies have figured out how to build cheaper buses. I think that the business model of spacecraft as a service is coming into the realm of the possible. We want to figure out whether we can do that. Again, we want to get more science or different science per dollar. The same is true, of course, as we go to the moon. We're using a service model with our commercial lunar payload services. In astrophysics, I think the most important impact that we're going to see is the emergence of large launch systems. Because many of the constraints that I just talked to you about relates to constraints that relate to the size of the launch vehicle, the ability for it to throw. The second piece that I think is really important is servicing and an assembly in space. Once these two tool sets are there, everything we're doing next changes fundamentally. So those are things, and frankly, I'm looking at commercial companies to provide that. The leadership of that is in the commercial space in many of these areas, not all, but in many of them is in commercial space, so we're looking at them. Now, I would not be surprised is if even companies, launch companies, basically saying, hey, or non-for-profits forming, it's like, let's build a cheap telescope that's really big and just see what we can do. So I'm interested in that. A number of companies have come to me and it's like, go for it. Let me figure out whether I can, at the back end, be a secondary market user for that, right? Because if the data were there, could we make it available for the science community? So that is still very shaky, very wobbly, but for me, I think what we're going to see in the next 10 years is a number of developments that make what I'm just saying right now a lot more likely. Thanks, everybody. Really excited. Thanks, Dave.
Wow, that was just amazing. Thank you so much, Dr. Zurbuchen and your team, and really congratulations to all of NASA and the Webb team on what you've done. I wrote down what I was going to say after that, and it doesn't work. It's just wow. That's all I have to say. So thank you. Thank you for taking the time today. Thank you all for being here as part of this. Before we break for lunch, which is right here in the room next to us, very quick, and then we'll resume at 1 p.m. I just want to again thank the partners that make this event possible. Advanced Space, AI Solutions, Blue Origin, Boundary Stone, Bryce Tech, the Brooke Owens Fellowship, Relativity Space, Rocket Lab, Space Intel Report, Virgin Galactic, Voyager, and the Z Factor Fellowship. So thank you to all of our partners and supporters. We'll break now. We'll resume promptly at 1 p.m., so please have a good lunch and do some networking, meet some new people, and we'll see you at 1. Thank you.